Okay. Can everyone see the paper? Just
Yes.
give me okay, cool. Before we start, I wanted to ground this paper a little bit in application. So they talk about and which they do in the introduction anyway. They say that there's a lot of situations in real life where you might need to model a dynamic graph, which is social network communication, financial transaction graphs, and longitudinal citation data. Those are the three that they give as examples. And the way that they describe a dynamic graph here is essentially you have an initial graph, which is a set of nodes and edges, and then over time, not with a fixed time step, you're going to get events, which are modifications to the graph, or something they call communications. And a modification to the graph would be either you add an edge between nodes, or you add a node which you connect to another node through an edge. So those are the two types of associations that can be what they call associations in this paper. And then communications are when you two nodes are not, like, there's no structural change to the graph, but two nodes want to pass information between each other. And I'm starting out in the explanation of this paper with that because I think that's actually something that took me a while to. First, I was like, why is this in here? Because, for example, if we were to apply this paper directly to our data, there's no associations. There's no communications. But what this comes from, just so maybe that I find if I can ground it in an example, it's easier for me to understand things, is, for example, one of the data sets that they have, they call social evolution. Let's see if they describe, there's a question here, which is, how about removing nodes or edges or changing node or edge features? So actually in the paper itself, they don't, they assume that the nodes, the node features can only be used in the initialization of their method. So your initial representation at T0 could be node features, but they don't really handle the case where node features changes. And they hint to a method which they point to in their appendix for how you could incorporate edge features in. But they don't really deal with these cases of changing node or edge features. So yeah, they don't deal with the case of changing node or edge features. They just point to how you could maybe incorporate edge features in during initialization of your dynamic process. And then for removing nodes or edges, they actually say in the conclusion, this method can't deal with that, with those types of what I would call actions again. So modifications to the graph, but there are some clear ways forward which you could deal with them. So this paper actually only deals with the situation where you have a graph and you are adding nodes or edges to it. And how would you model that process? Which I think I'll point out that maybe that seems like very limited, but it's because the problem itself is so complicated that they had to do a lot of they had to limit the problem in terms of like the scope of the research project, because otherwise they probably wouldn't have been able to find anything useful to deal with the massive amount of different ways that you can modify a graph. But anyway, so they don't really deal with those. But so one of the data sets that they perform their experiments on is called social evolution, and I think it's where do they describe it? Apologies. I'm just trying to find where they describe the. Okay, social evolution. They don't really describe it, but basically it's a community that changes over time, and the reason why there's associations versus communications is, like, for example, take Facebook. I think you could think of and you have your set of friends, and a communication could be that you message someone who's not in your group of friends. So essentially you're messaging someone who you're not connected to. And then association would be like you actually become friends. So there's like a friend request that gets accepted. And so that's actually, for me, a really key part of this paper. In fact, like the key contribution, that one of the key contributions that they argue about is that you have these two processes by which a graph changes over time, and they're coupled and they affect each other, and consequently the method that they propose. But you know, there's a lot of situations where you don't have both of these processes, which is like you don't have communications essentially, which are in a way often probably precursors to associations. So often people will talk to each other before they become friends, for example, on Facebook. But in a lot of cases, you don't have that. So anyway, I hope that makes clear what's the difference, what an association is, what a communication is, and why both of these are modeled in this method. Yeah. Let me just see if there's no questions. Cool. So yes, they're trying to model, as a last introduction to this paper is about representation learning. So the idea behind this is that you might have a task that you want to train a model to perform inference on, but you want to train a model to represent your graph or the nodes in your graph before you train it to do this task, in order to get a better representation or a more useful representation for performing inference. And so they provide an unsupervised method in order to train in order to train your task, train an encoder for your model, for your graph, and then you can use that in order to learn as the input to a model that you're learning to perform some form of inference. And again, so over here they present the two types of changes to a graph. One is a topological evolution, which is, like I said, adding an edge or adding a node and connecting it to an existing node through an edge. And the other one is a node interaction, which is where there's no additional edge. There's just like some kind of interaction. And again, I think that only happens in a subset of dynamic graph problems. And like I said here, they're saying modeling the interleaved dependencies between these nonlinear evolving dynamics processes is a crucial next step. So they're saying that modeling the interdependency between a history of topological evolutions and node interactions is important for getting a better dynamic graph. Another element of their method, which they argue is important for getting good results, is that they model things in continuous time. So the way that it's presented, I haven't gone a lot into the related work, but the way that it's presented is that if you're doing a discrete time approach, you basically get these snapshots of a graph that I guess maybe you can have possibly be more than one change to the graph at once, and you're trying to come up with like representations of each, and then you maybe train a dynamics model or a transfer function to go between them. But they say over here that these approaches tend to preserve and code very limited structural information and capture temporal information at a very coarse level, which leads to a loss of information between snapshots and lack of ability to capture fine-grained temporal dynamics. So this is the reason why they don't like this method, and then that's why they go towards the continuous time approach. And really, you still have discrete events in the continuous time approach, so your graph gets modified discretely in time, except in the secondary case, you don't have a fixed time step like you would in the discrete approach. I hope that, or you're not assuming a discrete time step, which you are with a constant time step with it, like you do in the discrete approach. So you could have something that happen at time 10, and then 10.2, and then 15, and so on. And so when they talk about in related work continuous time approaches for modeling these changes in a graph, they say that you can model time at a finer time granularity, but the existing work only can approximate simple structural change or they're using simple temporal models. So they're basically saying that there has been some work in this area, but it's not super well developed. And again, moving back to this idea of associations versus communications, and if that's not clear what that is, please just stop me, because it's really, I think it's really important throughout this paper to understand that difference. They say like these two processes that modify a graph happen at different timescales, and so you need to express them at different timescales, otherwise you're not going to get an accurate dynamic model. And they call their proposed process like a latent mediation process, which again, I think is a little bit, it's probably the correct word for it, but actually the way that, and we can go through this later, or we will go through this later, the way that they're actually modifying the representations over time is like you have your representation of a graph at time t, an event occurs, and then you update it based on that event. And they just have a different update rule for an association versus a communication. Because the way this mediation thing looks like, it looks like there's some kind of feedback loop, but to me, there's not a feedback loop if you take into account time, because you're always moving forward in time. Anyway, yep, so that's a little bit about the previous work.
I have a quick question. Yeah. Does the timescale parameter that they use, or just the timescale between the two processes, does that have any physical meaning or interpretation?
Yeah. So let's go. Well, the physical interpretation of it is it's like the rate at which events occur based on, and let's just jump into this part of it, which is temporal point processes, because this is like the key point of like the key idea, or one of the key ideas in the method. So the idea is that, like I said, you can modify the graph with two actions, a communication or action, or an association action. Let's just say you can only modify the graph with one action. And what you do is you model this action occurring or as a temporal point process. And so a temporal point process is, I'll just read out the first two sentences. So stochastic point processes are random processes whose realization comprises discrete events in time, T1, T2, blah, blah, blah. A temporal point process is one such stochastic process that can be equivalently represented as a counting process. So because the action is always the same, you could just count the actions that have already occurred. That's kind of what they're saying by these temporal point processes. And you describe a temporal point process by its intensity function, lambda of t, which is a stochastic model of rate of happening events given the previous events. So lambda takes into account the history. So the event, like basically the times at which events have occurred in the past, and it will tell you the likelihood of a time occurring in the future. There's two components to lambda. So lambda itself, it says over here, is the conditional probability of observing an event in the tiny window dt to t dt. So actually, I look at lambda as the probability density function of an event happening at a specific time. And then they also define a, and I actually think there's a typo here where I've highlighted this d, that I think it should be dt, but it just says d, but maybe I'm wrong. And then so lambda is the conditional probability of an event happening at time t, or the probability density of an event happening at time t. And then they define something they call the survival function, which is the probability is, I'll just stop, is h just the variation of n?
Sorry, so I just like the dn, is it just the variation of n? So I don't know.
Yeah, maybe it is just it's the variation of n. You're right. It's the expected variation. Yeah.
Yeah. Go on. Oh, sorry.
No,
yeah, I thought it was dn by dt is equal to lambda t. No. then they multiply through by the dt. I'm not sure.
Okay, yeah, that makes sense actually.
Yeah, it's the standard point process, really, right? Is it any parameterization on that lambda, or is it uniform across the path or the whatever it is acting on?
So the method itself, it defines some characteristics that the authors want for the stochastic process, and they define the parameterization of lambda based on that. So we'll go over it later, but there is a parameterization of lambda.
Yeah, because if I remember that this communication, was the communication literally just an event, or was it also an event that carries some sort of data?
Just an event, because they view nodes as being featureless in their method that they describe, and they view there being only undirected edges. So you can view an event. That's why you can model each event as a counting process, because there's only one type of action essentially in each case. And then they define this survival function, which is just the probability of an event not occurring between time t of n and t. And so they're saying the conditional density that an event occurs at time t is just lambda times s, which makes sense because it's saying what's the probability of an event happening at time t, which is lambda, times the probability that nothing happened before that point, between like tn, which is when the last event happened, and the current time.
So this is where it gets a bit confusing, right? Because the moment an event happened, the process doesn't change, right? So why wouldn't it keep on going?
It does change. So your history changes. So the function lambda changes.
Yeah, lambda changes, but why the multiplication with a survival function when there's nothing really to survive? It's just keeps going like it might just trigger the next event.
Sorry, could you say that?
Or is that because lambda is actually a function of lambda itself could be a function of that event happening?
Yeah, lambda is a function of all the previous events that have happened.
Yeah, because I think, right, so if lambda is the function for a message passing, and so if a message passes between node u and v now, it can yet pass another one again in any piece of time, right, going forward. So there is not that, because there's no decay in that sense. Doesn't really make sense to have a survival function there, I feel, because you would.
Okay, I see. Well, it's almost like you have a new survival function after every event, which is I think maybe what you just said, in the sense that like the survival function is just until the next event, and when the next event happens, the survival function is a different one because it's saying what's the probability of an event not happening in the future.
Yeah, I guess because the event itself would probably change lambda, and then if you were to know that happened already, then probably you would want to have a different function for lambda. So I guess that makes sense.
One thing I actually found confusing, and I think this is just because I don't have a strong background in this type of math, is like, so they're viewing lambda as a probability density function. And then to calculate the survival function,
it's not a probability density function. It's a intensity, right?
Well, yeah, I guess they just make the rule that lambda has to be positive, so it's not a density function.
Yeah.
But that's kind of how I view it. But probably that's the wrong way, and that's why I was just, when I saw this, they're computing probabilities off of lambda straight, and then to calculate the probability of survival, they're doing an integral with an exponential. I was like, I don't see how these two can be related, but probably I just need to read about survival functions and I'll understand it.
Yeah, I struggle also to make sense of this exponential, because so if it's like they're doing 1 minus the probability that something happen, or 2 events happen, 3 events happen, and so on. But then the lambda depends on the previous events, right? So this
Yeah.
exponential is not really an exponential, it's something more complicated, right?
Exponential is really just saying that the rate of change function is proportional to the intensity of the process being there to begin with, right? So it's really just the integration of the SDT being lambda, and because lambda can be time dependent, this is generally a true equation. Of course, doing the assumption that t at t equals 0, s is 1, right? So that is, or at t equals tn, s is 1. Right?
That's the case. Yeah. Okay, that makes sense. And then, but so, okay, I could see how this is trivially true because it's 1 at time 0 and it just exponentially decays.
Yeah.
Okay. And it like the lowest you can get is 0.
Yeah.
Okay.
So the SDT is minus lambda dt.
But what that means to me is that this is just a functional form that works for the properties they want of a survival function. It's not like some kind of derived like the correct survival function. Maybe there's a more complicated one that fits whatever process you're modeling better. Would you say that's true or no?
I think that the difficulty is, or all the complexity ultimately sits in lambda.
Okay.
So how lambda is behaving, and essentially all the complexity, yeah, all the action is in there. No, I'm just trying to think of what happens here is that we by having this we don't really have a feedback effect, right? So we know typically if an event happens in such a network, probably some change can happen that can create more events. And by having this form, you sort of prohibit this, right? By having just a rate, because now it's I think the assumption is that events are sort of independent because they are at the end of the day pure Poisson noise, right? And I think that's probably why they put in this dependency on the survival probability explicitly. Otherwise, you probably wouldn't get any self-amplification effects of any sorts. I'm probably not very clear at all.
I kind of got what you're saying, but I'm thinking to myself, let's get into what the lambda function is, and we can discuss this again, because maybe with some more detail, it will become easier to flesh out some of these questions. So we'll just go quickly into the notation. Like I said, they assume that all the edges in the graph are undirected, and no worries. See Arvin. Good, less questions. No, I'm joking. Hopefully you guys have a lot of questions as well. So I think one important thing is about how they model an event. An event is a modification to the graph, and all the events, like both communication and associations, are modeled by this tuple here, where U and V are indexes of nodes, and T is the time at which it occurred, which can be any positive real number. And then K is whether it's a communication or an association event. I think K equals 0 is an association event, and then K equals 1 is a communication event. Here represents an abstraction of scale. Okay. I won't go through all of this. Let's just talk about lambda. So, like I said, the way that they model this whole process is as these what is they called, temporal time processes, and or temporal point processes, and the temporal point process is completely defined by lambda. So their lambda here is a function of like two nested functions, f, which is up here, equation 3. So this is where the rate of the rate function or the timescale function c comes into play, and it's a learned parameter, and it's what determines like the rate at which you expect events to occur. C is a constant. It's constant, which means that in the sense that it's not time dependent, it's time independent, which means, for example, a couple of things. One, even though it's a learned parameter, that means that you assume that these events occur within your problem space with the same frequency, no matter what graph it's on. And two, it's time independent, which means that you assume that the rate doesn't really, of like the event occurring, doesn't really change with the time, like with the amount of events that have occurred before. But I think that X and the way X is calculated has some mitigation on that fact that this is like constant with respect to time and across graphs in your problem space. So that's lambda, which is over here. I mean, so that's phi or f, and then g within it is you take your current node representation of node u and your current node representation of node v, and then you concatenate them and multiply them by a vector, which is you basically perform a dot product on them. So you calculate like the difference between them. Again, this is omega is a learned vector, but it's constant with respect to time. And these are a couple of the simplifications that they do in this method, which I found quite interesting, because it's like, wow, this is actually pretty simple in terms of its parametrization, but it seems to be pretty effective in terms of the results. So essentially, they're just saying like, how close in magnitude are you to this vector and direction, and that will determine the rate at which the next event occurs. So two representations which are similar. Well, actually, it doesn't matter how similar they are. Yeah. Anyway, let's see.
I have a quick question.
Yeah.
So they have this t over bar. Is this t minus dt, or is it just any data point at a time before time t, or
T
I'm
over
not sure.
bar?
Yeah, because it says it signifies time point just before, but what does that mean?
Yeah, that's a really good question. I should have explained that. So basically what they're saying is T underbar is the time of the last event that occurred. And the reason why that's the case is because the way that they update they only update the representation of each node when an event occurs. So they don't have they're not actually continuously propagating the representation through time. They're just doing it whenever an event occurs, we update the representation in their algorithm.
Yeah, that makes sense.
So like I said, lambda is actually a pretty simple function, and really the meat of it, like it keeps going farther down in layers. The meat of it is like, how do you calculate the representation at each time step? And so we'll move on to equation 4. So the authors specified that there's 3 things that they want to see in their calculation of z in terms of like the calculation of z is essentially calculating is a dynamics function of the process that they're modeling. So one other thing that I wanted to highlight is, and hopefully this is useful information to you, is that the stochastic or the temporal point processes that they're modeling, there's one between every node in the graph, every node pairing in the graph, which is different. So it's not like the whole graph, like the way that they're combating this problem is by making it a pairwise temporal point process. And I think that's important because it's what allows them to, like the process that they're actually describing is super complex because of the fact that there's, like, you take the number of nodes and it's like there's n squared different processes happening at once to define this graph, to define the evolution of this graph. Anyway, so the way that they define the evolution of a node representation Z over time is, first off, they say we initialize Z to either be a random feature vector. They say it over here. The initial representation of node V may be initialized either as input node features from a data set or a random vector as per the settings. I thought it was interesting that they say you could just use a random vector, but I guess you're training your model to calculate these representations. So they'll say like the model will adjust to getting random initializations. But anyway, they say that the dynamics process needs to have three properties, and that these are what I would like. They're not bad assumptions. They make a lot of sense and they're intuitive, but these are assumptions that the authors are making. So the first one is self-propagation. And they say self-propagation can be considered as a minimal component of the dynamics governing an individual node's evolution. So it's saying that somehow there's part of the dynamic process is that you're going to change when an event occurs just based on what you're, yeah, that's Vahan saying probably random initialization if there are no node features in the comment in the question, and in the chat, and yeah, that's what they're saying. But so they're saying like every time there's an event, you're going to change what your representation is just based off of what your current representation is, which I guess makes sense. I think makes sense, but at the same time, I could see cases where that might not be the case. But I guess then they'll say, well, then the model will learn to have a weight matrix of 0. The second one is called Excitationist Drive, which is, it says some exogenous force may smoothly update the node's current feature during the time interval. So this is, again, assuming that there's like some forcing function in the dynamics that's that just changes the node features over time. I thought this one was interesting because, again, I don't always see that this would be the case, but maybe, again, they're assuming you'll just learn a 0 weight matrix for exogenous drive, but also because the exogenous drive is like the driving function is just dependent on like how long between events, which means it's applied to every node and every graph in the problem the same. So like basically it's saying there's the same forcing function between every node for every node, and it's just based on time, external forcing function of the dynamics. And the last one is the one they spend the most time on, which is they're called their localized embedding propagation. So you have these two terms over here, which are kind of like independent of the neighborhood, although Z, the previous Z is calculated using the neighborhood. And then the major one is you have your like your localized embedding propagation. So and they say it over here, H, the function H, which is your localized embedding propagation, is the output representation vector obtained from an aggregator function on nodes U in the neighborhood of the function. Okay, so that's how they calculate the representation, and then we go to the final layer of this function, because it's like you can see we had lambda, then we defined f, then we defined g, and now we defined how z is updated, and the final step here is how do you calculate h. And so the way that they calculate h is that they use a temporally attentive aggregation function.
Sorry. Okay, quick question. So I get the update for the embedding Z, right? So the self-propagation is just sort of, you take the previous update and then h-struct is your aggregation. But then with the drive part, I feel like it has this assumption of, if you have a lot of time between two different events, then there's going to be a lot of emphasis placed on sort of, you're going to weigh this WT by quite a lot. And if the time is sort of really small between events, you're going to, if you take it to 0, you're just going to be like, that time's going to go to 0. So I'm trying to think, what's the sort of idea behind that? Why did they?
I honestly, that's what I'm saying, that these properties of the dynamics model that they're defining are assumptions that they make. I don't actually see a strong like a strong justification for these exact properties. I could see just the idea that, like, for example, on the data sets that they're testing this on, there are communities made of people who change over time. And so maybe there's some idea like we need something that models this change over time, which is isolated from the system itself or something along those lines. But these are all just ideas or justifications that I can come up with. Maybe a reviewer comment that would have been useful is to have a better justification of each of these properties, because I don't personally see why these properties are so necessary. Or like
I was thinking,
yeah.
Yeah, I was thinking maybe because sort of if a lot of time passes between events, then these sort of events are pretty rare. So you want to place a lot of emphasis on those events. So maybe that's why. Like, I guess they must be important. So I guess.
I think that the better question is like, are these assumptions generalizable to all problems that fit under the problem formulation that they're using or not? Maybe they are. Okay, so the last step is in defining their method is this temporally attentive aggregation function, which is actually pretty simple. All of these things are like all the different parts of this model are really simple, which is one of the things I appreciated about it. So, okay, what's their aggregation function? Essentially, we'll just get to that first. Where is it defined? Okay. Oh no, it's here. Okay. This is the aggregation function they use. So they take Q is some weighting of, oh wait, sorry, we'll have to go one by one. So let's start with the inner H, like HI. HI is a weight, like a linear mapping between. So you take all of the neighbors of a node U and you get their representations. You pass that through a linear mapping with a bias term, which is what you get HI. Then you multiply each of them by Q, which is an attention mechanism, essentially weighting how important each of them is. And then you pass that through an activation function, sigma, and then you take whichever representation has the highest activation, and that's the one that you use as your input to. That's what you use as hstruct. I'm just thinking to myself now. I guess it's. That's one thing that's a little bit confusing to me now that I'm looking at this is that they're taking the max representation, but what are they taking the L2 norm of the representation that they calculate, or how does it become a single number that they can take the max over? If anyone has an idea about that.
Is just an activation function or something?
Yeah, but to me, my understanding is that the output of hstruct is a vector. And if that's the case, like, how do you define the max of a vector? Usually it's by saying like, it's L2 norm or something like that. But in order to take the max, you need to comprise your options down into a single number for each. And I don't see how they're creating a single number for each of their representations, because they're multiplying, like, HI is a vector and they're multiplying it by Q, which is a scalar, and then they're putting it through an activation function.
Oh, but it's the max of a set, no?
Yeah, but how do you define the max of the set? If each element in the set is a vector. Oh, okay, sorry. It says it over here. My bad, I should have read it. It says, by applying max pooling operator element-wise. So basically what they're doing is they're taking all of the representations and taking the max along each dimension and using that as the representation. That's how they're doing it. So in fact, it's actually a mixture of all of the different representations based on which one has the highest maximum value in each dimension. And they say here we found max to work slightly better as it considers temporal aspects of neighborhoods, which would be amortized if mean is used instead. I think that they just tried this and it worked better. I actually don't think that's a great explanation of why you should use max as your as the way that you do aggregation over your representations. But anyway, that's the struct function, and that's the, well, I guess the second to last step. There's one more beneath it too, which is like, how do you calculate Q, which is your like attention. And the way you calculate Q is you use your adjacency matrix at the current time to figure out what are the neighbors. And then you have another matrix S, which is your weighting for each of the different neighbors. And that is updated based on this algorithm 1 here, which has a different update rule for communication versus an association, which we will not go through, or we can go through later, but I want to get to the actual results. And then the last important part is how they train this model. What's the unsupervised objective, which is this function here. What it's basically saying is that it's maximizing, if P are the events that have occurred, like P are the observed events, it's maximizing the probability of each of the P events occurring, I'm guessing at the time at which they occur, plus the probability of all the other events not occurring. So they're trying to maximize the probability of one of the event that they observe occurring and minimize the probability of all the other possible events not occurring, since the probability of all the other events not occur, since there's so many probable events that could occur, like in some cases millions or hundreds of millions, they just use Monte Carlo sampling to calculate that integral. Does that make sense as what the training objective is doing? Kind of, yeah. Hopefully. Okay, cool. So in terms of experiments, they test their method on 2 data sets, the social evolution data set and the GitHub data set, which have different character, yeah?
So for the question about the exogenous drive, I was wondering, like, if you remove this, is this just basically a discrete time system then, without the exogenous drive? Because this is where the only place where time interval seems to play a role.
That's a good point. I didn't think of that. Maybe that's why they include it. I'm not sure, but that could be a good reason for why they're including it, because their whole point is that using discrete time steps isn't useful or isn't as good. Maybe this was just the simplest way that they could create like a system that uses continuous time. I don't know. That was a pretty poor explanation. Do you want to talk about it more, or should we keep going?
No, that's good.
Okay, cool. But I think that's a good observation. Cool. Again, social evolution data set, GitHub data set, and they choose a number of different methods or baselines to compare their method against. DyREP is their method, and then you can see the other methods that they compare it to, and what the differences are essentially. One point they make is that only their method and another method can model communications, and it seems like modeling communications is important for this problem, because for these 2 data sets, because the 2 methods that can model communications almost seem to always outperform the other ones. And then GraphSage does pretty well on some of them. So they compare their methods on 2 tasks for both of these. One is dynamic link prediction, so predicting like a link that should occur in the graph, and the other one is event time prediction. And I just wanted to go over the 2 metrics that they're using. One is mean, where is it? Sorry, not mean absolute error. It's, oh yeah, mean average rank. And so what they do is they have, when they're doing these tests, they have a set of edges which should occur, and they have a set of edges which shouldn't occur. and they rank them based on the likelihood that's outputted by this model, temporal, like point process. And then they calculate the average rank of all the positive examples. So like the average rank of a positive example in the social evolution data set for their model is 10. So on average, it's ranked 10th in the list. And then in GitHub, the average rank is like 2,500. And then the other method is hits at 10, which is you take the top 10 recommended actions, like adding edges or nodes, and what percentage of those are positive examples, so like actually occur in the future of what you're seeing now. They don't actually report the hit at 10 until unless you look in the appendix, but the results are similar between the two of them. I just had never heard of these metrics being used before now, but I think that what they do is they highlight how hard this problem is, because they can't just report like accuracy, for example, like top 1 accuracy or top 3 accuracy. They have to use like mean average rank in order just to give you like a metric on which the answer is not like the value is not 0 for all of the different baselines that they have. But anyway, so what you can see is actually that their method, DyREP, just outperforms all the other methods on both data sets in terms of mean average rank. And then they also compare their method in terms of time prediction performance. And again, their method does way better than the other two methods. One thing that I think is a little bit misleading about this is they call their method unsupervised. But in my opinion, the training objective that they're training for is to like be able to predict the time at which events occur and then also which event it is. But so in a way, even though they're calling their method unsupervised, they're evaluating it on one of the tasks that they're training the model on. So maybe it is unsupervised, but they're also evaluating it on one of the tasks. It's not like a downstream task that you're using the representation for. It's the task that you're training the model on. But they really outperform the other two. Like they really outperform what is MHP, and then they outperform the other method that they're comparing against by a lot too.
I have a question. I don't know if it's super important, but in the comparison with the other approaches, they have graph information and it says second orders, first order. But is that taking in sort of the second hop, first hop, or what does that mean by second order neighborhood?
Yeah, that's exactly what it means. So second order, the reason why they call it second order for this method, DyREP, is because so you say you add an edge between two nodes, and then the method that they're using passes information from that node that you just connected. And what's important there is that that node has already aggregated its neighborhood when it's passing that information. So you would think of it as maybe first order because you're just getting information from the node that you've connected to, but you're actually getting from all its neighbors as well. So that's second order because it's 2 hops from the node that you're aggregating information into. First order would just be like direct neighbors.
Yeah, that makes sense.
Okay. Yeah, I was wondering that too, because when I read the method, I was like, this sounds like first order to me, but then I realized it's second order because the aggregation function takes into account the neighbors of the edge of the node that you've just connected to. And then they compare their method in terms of t-SNE, like in terms of how much it separates the points, like the nodes in the graph. But and like their argument is that if you look at GraphSage versus DyREP, that you can see a lot more clusters. But like I was thinking to myself, are these meaningful clusters? Like I know it'd be really hard to to color all of the different nodes by edge. But I'm just wondering to myself, like, what if these clusters, like there's more clusters, but what if they're just random nodes? Like, what if they have no connection to each other in the graph or something like that? So I didn't really feel like these results were super useful, besides the fact that they look good. Also because, like, you can run t-SNE twice and you get very different results. So how do we know that they haven't just run it like 60 times until they got the results they want? We don't. There's like a little known fact that there's this one of the fundamental papers in machine learning is this like Min et al, where they introduced DDPG, which is like a reinforcement learning method, and they published it in Nature, and they have like this amazing t-SNE plot that looks really good. Supposedly they had to run t-SNE on this massive data set like 1,500 times or something to get that plot. So, and that means that it probably cost, because the data set was so massive, like, I don't know, $1 million or something like that. It's just like, but the fact that they had to really try many times until they got the t-SNE results they were looking for. Anyway, so anyway, that's the method. The key idea is that they define the dynamic process of the graph changing as a temporal point process, and in fact they define it as two temporal point processes, which like together keep changing the graph. One thing that I think is a limitation of this paper is the fact that for each different action that you can change the graph with, you have a different temporal point process. So if you didn't have two, but you had like thousands, this would probably become an intractable method. But I do think it's really interesting, and I'll just open it up for questions in the last 4 minutes.
Maybe a simple question, Peter, but I didn't quite get how did they, why are they comparing against GraphSage and the other GNNs? Because they don't do anything about the time steps. What kind of comparison is that?
Well, okay, that's a good question. Pointing to the fact that maybe I need to work on my presentation. But so the reason is because the whole idea of their method is that their representation that they create is passing information through time about the graph, and then you use that representation in order to on some downstream task. So they wanted to compare it to, like, if you just had the graph at that time step and you only took into account that information, then how good would the model be at that downstream task when you train on it? So it's basically saying, if you have a representation which takes into account the changes in the graph over time versus one that just looks at the graph at the current time, will you perform better or not? So it's kind of like a baseline that's there just to show that there is an improvement in performance by taking into account all this extra information.
Okay, that makes sense. I thought they tried to use the normal GNN methods in a comparison with some other time series model to learn. So that makes sense.
Oh, one other thing I wanted to point out is this method is only applicable when you actually have like timestamps of the graph being edited. So you need to have, like, no, at this time the graph was changed in this way, and it has to be pretty fine grained. It has to be like this node was added, this node was added, this node was added. So because the problem is, if you have 10 nodes added, I think that how many different ways are there to add 10 things? I think it's like 10 factorial. Yeah. So unless you have the exact number of, like, the exact time and order in which you add all these edges, you're basically going to have to make up a data set where you don't know what those are. Cool. I really like this paper because I've never really looked into temporal graphs before, and also it has good results. So maybe I was a bit harsh, but I think it's a good contribution, especially because of the simplicity of the model versus the results they get. So thanks everyone for attending, and hopefully see you next week.
Thank you. Bye.
Thanks, Peter.